Okay, welcome everybody to the presentation for RedPoint. I'm Will, and along with my co-creators Ben and Charles, we built RedPoint, and here's a sort of talk to explain what we built and why. So, what is RedPoint? So it's a computational notebook that's optimized for note sharing. So it's a place where you can execute and write different programming languages in the same document. You can describe your code cells with descriptive markdown, and it runs in the browser. So it's web native and open source and hosted, so completely free and open to use. And the code is an MIT license. So if we take a step back, we can ask what just actually is a computational notebook. So the first major point is that it's a cell-based design. So you can see you've got cells of code interspersed with cells of descriptive rich text where you can stylize and describe what's going on in the code. And the next point is that the code is living. So you can run the code that you've declared in one cell. They're connected in state, so you can see you declare a function, say hello in the first cell, and then in the cell below it, you can invoke that function. So it's a living document. And when you combine these two features, you create what's called a computational notebook, a computational narrative. So it really is great for sharing notes. You can combine all these nice rich descriptions with living code. And that just makes them really ideal for sharing or taking notes for yourself for later. And that means you don't have to switch context to run the actual code. So most programmers are familiar with traditional note-taking applications, like here's an example of BoostNote. They got a really great focus on note organization, but one of the drawbacks is that when you write code in a traditional note-taking application, that code is static. So if you want to run and execute that code, then you have to copy and paste to another environment. And that context switching is something we're trying to avoid. So these are also generally not web native. So in the example of BoostNote, if you want to reference your notes on your cell phone, you're going to have to pay for an application on your phone and pay a fee. So here we have Quiver on the left, an example of a side-by-side comparison of a note-taking app Quiver on the left and a computational notebook observable on the right. So Quiver uses the cell-based design with these markdown cells up top and a code cell on the bottom. And you can see the nice syntax highlighting, that's great. But again, that's static code. So if you want to run that code, you're going to have to copy and paste that somewhere else to run it. Now on the right, we can see an example of Observable, which is a computational notebook that's geared towards visualizations. If you noticed in the GIF earlier, there's code at the bottom, and these sliders here are manipulating that code, which is rendering that data live in the browser. So it's quite powerful. We built RedPoint to try and bridge the gap between these two solutions. The syntax highlighting and note organization focus are great of note-taking apps, but with the drawbacks of the code being static, we felt there's some room for improvement there with a tool. And these computational notebooks on the right side of the spectrum, like Observable, RStudio, and Jupyter Notebook, they're geared towards data science and data visualizations. And they're really powerful tools, but the complexity level gets higher. And some, like Observable, use specific language dialects. So although Observable supports only JavaScript, the flavor of JavaScript that they support is actually proprietary and unique. And that makes it not quite so suitable when your goal is to take notes for regular vanilla JavaScript. And if you notice too, of all these options of the major players, only RedPoint and Jupyter Notebook are completely free and open source. And speaking of Jupyter, which is a big player in the data science field, it has this issue of complex state, or what we consider an issue. So if you have an example here, this is Jupyter Notebook, and in the first cell, you assign the variable x a value of 42, and then you log out the value of that variable in the second cell. You might expect it to log 42, but actually here we produce an error, because if you see in the brackets here, the first cell executed is this log statement. And because this was not run, this cell up here, we get a reference error. If you take a happy path, You remember to execute the top cell first, then you remember to execute the second cell in that top-down order that a programmer might expect. You'll get sort of what you might have immediately expected here. You get the return value of 42 up here and the output 42 down below. But also notice that there's no real differentiation between this return value up here and this output down there, which is a fairly important distinction for a program. We continue with the example. We reassign the variable in the third cell to 99 and we run that. So that looks pretty normal. But now if we go and rerun that second cell again, it's going to log out that updated 99 value. And this is a pretty simple example, but it just shows you how that flexibility might lead to some confusion because the actual state of the program is sort of hidden behind the scenes with the internal mechanisms. So even in this very simple example, if you were to share this notebook with somebody else, they might be confused as to how we're logging a value of X that's 99 on this cell. So we built RedPoint to try and bridge that gap, like I said. And we felt that notebooks are really powerful tools for what they're designed for, but we felt for sharing notes and taking notes for a programmer in a vanilla language, that building this tool would be helpful for people to just share code easily with a really low barrier to entry, and so that they could minimize that context switching. Also, it's a completely free and open source project, so the code is available. We have instructions if you'd like to self-host with your own organization. I'm going to go along and just outline sort of the rest of this talk. I'm going to talk about a few of the features we were able to implement with RedPoint. And then Charles is going to take over and talk about the network architecture and some of the decisions we made there. And then how the user experience we desired informed some of the decisions we made. Then Ben's going to take over and talk about security and resource management and some of the challenges we encountered there and the ways we addressed them. And finally, following up with a description of our internal system architecture and how we built this and some of the tools we used. So some of our high-level goals were that we wanted to create an easy to reason about scope and state with a clear display of code execution information. So outputs have a nice green background, return values have a white background, and any errors will have a red background to make a more presentational option for sharing code with others. And we really wanted to leverage the web native status. So one of the features we were quite excited about is that our notebooks are multi-language within the same notebook. So you can see in this example, we've got a Ruby cell with a simple statement, JavaScript cell, and also Python. And then with one click, you can run all of those cells. So currently we support those 3 languages. We were able to interact with APIs being web native and in the browser. You can hit an API endpoint, get that data, it gets sucked right into your notebook, and you can interact with it computationally. Also, webhooks, we provide a URL endpoint so that if you subscribe to a webhook provider, that when an event on another server generates a JSON payload to our servers, we will then take that data and put it into your notebook so that you can examine it and interact with it programmatically, just like an API. We also wanted to leverage being web native that we can support mobile devices like tablets and cell phones, so you can get the same kind of experience on your cell phone or tablet as on your desktop computer. And that means if you get inspiration for a coding idea while you're riding the bus, you can type out that code and run it on your cell phone, and then you can save it for later or share it with somebody else if you're looking for help on a problem that you're struggling with, or if you just want to reference it for later. And just to remind you, this is a completely free and open source project that we have hosted online, and we're going to share that link with you later on in the presentation. So now I'd like to pass this talk off to Charles, who's going to talk a little bit about our network architecture.
All right, thanks, Will. So before we get on to the system architecture unique to our application, I will address some of the early questions we faced that provided a nice foundation for the rest of the project. So the first question we had to answer was, where will we execute our user's code? Whether that's on the client side within the user's browser or on the server side. So we knew that how we execute code and render its relevant data would depend on where that code is executed. So first, To execute code on the client side has some ups and downs. The primary benefit to client-side execution is that we have a very fast, primarily client-side application without any latency incurred in a round-trip visit to a server. The downside to client-side execution is that our client's resources are going to vary widely. And since we want to provide a similar experience for mobile users as we do desktop users, it just presents just an issue there with performance. And the biggest drawback to client-side execution is that browsers only support JavaScript. So unless we compile all supported languages within the browser, we are only able to run JavaScript code. Now, the other option is to accept the user's code as a post request, for example, on a server and execute that code server-side, which allows us the benefit of supporting many languages without the need for in-browser compilers. We also have much greater control over the resources that power each of our user sessions. And the downsides to server-side execution are the latency that I just mentioned and security. And we will talk about how we've mitigated these two drawbacks to server-side execution later in this talk. So given all these benefits and drawbacks, we decided to go with server-side code execution. And now that we know that we'll be executing our user's code on the server, we needed to decide how that data would be exchanged between client and server. In other words, which network protocol will we be using? So our early prototype used a simple HTTP protocol where the client would edit code in their browser and submit it for execution on the server. And during the execution of the user's code, we built a response object, serialized it, and returned it to the client for rendering. And while this worked pretty well for simple code, it presented a very poor user experience when provided with asynchronous user code. So in this example, we have some asynchronous user code that just logs a simple hi there. And over traditional HTTP, the client will not be able to render anything in their UI until the slowest running code has completed. So we are not able to send any messages back to the client and render hi, for example, until that 10-second timeout has elapsed. So we decided that we would need some form of a persistent or a persistent-like connection between client and server. And while it's meant to mimic a persistent connection, we only very briefly considered HTTP polling, which would be wildly inefficient if our client submitted code for execution to then rapidly poll the server for any results of that code execution. So that one was quickly scrapped. Server-side events do offer a truly persistent connection. However, the communication between client and server is a single direction. It's primarily used for subscribing to a data stream where messages are fed from server to client. So what we really needed was two-way communication between client and server, which is exactly what the WebSocket protocol provides. So this full duplex communication over a single TCP connection would allow our client to submit code for execution to the server, and for our server to send one or many responses back to the client. Another benefit of WebSockets is it allows us to fairly easily detect a client's disconnection, permitting us to free up computing resources associated with that user's session. And we also experience decreased latency when using WebSockets because after an initial HTTP handshake, there are no headers exchanged in WebSocket messages. So we have a little faster exchange of data. And the main trade-off to using WebSockets was the added code complexity. So here's that same user's asynchronous code sent over a WebSocket connection. And after that initial handshake and persistent connection is established, the code is executed on the server after it's sent from the client, of course. Code is executed on the server, And during the execution of that script, we're able to listen to data events on the standard out stream. And WebSockets then allows us to send messages as soon as they're available in that standard out stream. So now that we've covered the basics of our network architecture and network protocol, I just wanted to pivot a little bit and talk about a couple technologies we hoped to embrace as a web application. And as Will mentioned earlier, we do support interacting with API endpoints where the client issues a GET request to an API and simply hydrates a cell in the notebook with the incoming data. Now this synchronous interaction is fairly straightforward, and the interacting with webhooks is similar but slightly more complex, as it's an asynchronous interaction between two servers. Using our application as an example, we provide each notebook a unique endpoint that the user can then register with some external service that supports webhooks. And then when some certain event occurs on that external service, the external service posts relevant data to the user-provided endpoint. And so this asynchronous exchange of data is in contrast with that synchronous API request where you ask for some data and immediately get it back. And the biggest difference is that our system no longer controls the rate or quantity of incoming messages from that external service. So to limit the rate at which we store webhook data in our database, we implemented a buffer using a Redis message queue so that when a webhook provider posts some data to our system, we can enqueue that into this message queue where a background process dequeues data and stores it into the appropriate document in our Mongo database. Next, I'd like to talk about some of our desired user experience, since it really dictated how we executed code. So our main design goals were to provide a predictable scope and state across multiple cells of a given language, to have a very clean user interface, and to render results of code execution under the cell responsible for those results. So first, how do we share scope across different cells? We do this by sending over each cell of a given language to the server where the cells are combined into a single script. This allows the user to know that if they have declared a variable in cell 2 here, we see new year, we know that it will be in scope in the third cell. And one of the primary challenges in this section was how to get clean execution results. As we see in this example, we have the standard out, or the output of that put statement, in green. We have return values in white, and the error down below in red. So the two options we considered, or two options before us, were to take our user's code and run it through a REPL and parse out the relevant data that we'd like to render. And then the other option would be to build a temporary file and execute that file as a script. So we'd build a RB file for Ruby cells or JS, etc. So let's look at these. We know that there is a challenge when dealing with a persistent REPL, and I'll just walk through these two images, which are a similar example to what Will showed earlier. So on the left side, we have declared this variable word with the string value foobar, and we've executed the cell only to realize that we have a typo. So we fix the typo to foobar and re-execute the cell only to be given this syntax error. And as we've sort of discussed already, this is because we have a persistent REPL behind the scenes. So when we fix a typo and re-execute it in this hidden state, we've already declared word. Our solution here was to simply respawn the REPL for every code execution request, which provides a clean slate for every execution. The drawback here is that when one cell is executed and re-executed, we're reperforming computation of previous code cells, which we felt was a valid trade-off considering the predictable scope it provides. So if we were to rely solely on the results of passing our code to a REPL and executing it, we'd be dealing with a few parsing strategies to obtain those results for our clean UI. However, parsing a return value is fairly straightforward as it's the last line in this REPL's execution. Some drawbacks to using a REPL to get all our results are that REPLs won't halt execution when an error is encountered. Since we're just feeding line by line into a REPL, we're going to keep executing code even when we encounter an error. And also, if we want to obtain standard out or just logged output from some user's code, we would require some pretty heavy string parsing strategies unique to each supported language. So then the other option would be to build a file of the appropriate language and execute that script. This was pretty cool because it allowed us to listen to data events on the standard error and standard out of those processes, which was just great since it eliminated the need for any string parsing to get at those results. And another great benefit of executing scripts are that errors will halt execution. However, we no longer can obtain a return value from a script's execution. And executing a script would look something like this, where we take our user's code, create a script, execute it, and during that process, we listen to the standard out and immediately send messages back to the client as we receive standard out. And when an error is encountered, the script process terminates and we send in a WebSocket message that error back to the client for rendering. And again, we don't have any return value using this approach. So our solution was to combine both strategies, obtaining our output and errors from the script's execution and return values from the REPL. Using a JavaScript promise chain, we're able to reject upon any errors encountered within the script, eliminating the need to process any code in the REPL. So then finally, one of the challenges here was how do we know which cell was responsible for some output, since when the user submits their code to the server, we assemble one single script and listen to standard out, standard error. We parse the return value. We no longer have any notion of that cell-based origin. So to determine where some WebSocket message and its data should be rendered, we implemented a delimiter strategy. So I'll remind you that when the client sends its code to the server, the cells executed are combined into a single script. When that happens, we also include some language-specific log statements or delimiters, so that when the script is executed and we're listening to standard out, if we encounter one of these delimiter values, we don't send the delimiter's value back to the client for rendering, but instead we just notify the client that it can increment the cell that it will render any subsequent data beneath. And next, Ben is going to talk to us about some of the security considerations we made and management of resources.
Thanks, Charles. So as Charles mentioned earlier, there are some inherent security concerns that we need to address since we've decided to execute our user's code on our server. Some users might not use their notebook as intended and instead might try to run malicious code inside their notebook that could interfere with our host system, for instance, by trying to delete files. And also, since our system has limited resources, we need to figure out a strategy for managing those resources. And the first question we had to address is, how are we going to safely execute this user code? The first approach that we thought of was to essentially blacklist every possible command. In this example here, someone's trying to run RF, and so if we could anticipate that, we could check every command and just never execute the ones that were malicious. The drawback to this strategy is we'd have to be really creative in anticipating every possible harmful command that a user might want to run. And then we need to translate into each of our supported language, which isn't really that sustainable. And finally, if we misidentified some code that wasn't malicious, then that code would never run, and that would be a bad user experience. So we needed a different solution. And the approach that we ended up taking was more of a system-wide approach. We implemented Docker containers for our applications, which effectively allowed us to isolate each user's session. Just to give a brief background on how Docker works, you create something called a Docker image, which is like a blueprint for your application. And in that image, you define any dependencies, like for us, our language runtimes that we want to support. And then using that blueprint, you create as many copies of your containerized application as you want. And inside that container, there's a consistent environment for your application with all dependencies. And these containers spin up really quickly, which is really helpful for our use case where we're creating multiple sessions for users. And the way that this strategy addresses our security concern is that now a malicious user has their own session. So in our old model, if that user somehow manages to crash the session, it's going to impact all users. Using containers, on the right here, we see that we've got a terminated session, maybe due to some malicious code, but every other session is still active. And then another advantage of these containers is that each user gets their own copy of the application, so there aren't any remnants or artifacts from previous sessions. And we wanted to go further by restricting users' privileges within these Docker containers. So there's a default behavior. Each user sort of is performing as a user inside the container. And the Docker default behavior is to have that be a root user. Way too many permissions there for them to commit harmful commands. So first we made sure that that Docker user is a non-root user. Then we limit some other permissions, make sure that they can't do things like alter their bash profile. And finally, we created a custom folder for the system binaries that user will use. And inside that folder, we're able to whitelist the commands that we want them to have access to and keep restrict any access to harmful commands. And having implemented those layers, we still need to go a little further to protect our host system. And the reason that we need to do this is that even though Docker containers do isolate sessions from each other, they're not a true sandbox. And the reason for this has to do with the way that the Docker technology works. The reason that they're lightweight and fast to spin up is that they run directly on the host kernel with a pretty weak level of isolation between the two. So a malicious user could try to break out of the container and use a kernel exploit like a privileged escalation attack and then gain access to our entire system. So to mitigate this, we implemented a technology from Google called gvisor. It's an alternative runtime for containers, and it basically acts as another layer of protection around each side container, functioning almost like a guest kernel. So what it does is it intercepts any system calls that containerized application makes, and it re-implements them in its own safe and rule-based way. It has another advantage in that it effectively virtualizes the file system of the host so that even if a malicious user thinks that they're interfering with the host system, really they're just interacting with a copy and no permanent damage is done. And of course, this comes with a trade-off, that being that using this alternative runtime for containers consumes a little more memory. We did some load testing and we found that the impact was about 25% fewer for containers that our host system could support. And it even had a small impact on our notebook performance. But given this trade-off, we decided that it was acceptable to enhance our security profile. And then the last concern is how to prevent resource hogging and make sure that everybody has a nice balance to their resource use. And we can see here we've got one user who is running some computationally expensive code by writing an infinite loop. And if we don't have a strategy to balance resources, the default behavior of Docker containers is that they're going to consume as many CPU cycles as they can. So we need a strategy to mitigate this to make sure that others' users' code performance isn't impacted. And the solution here is to use Linux control groups, which are basically some settings that we can implement within Docker that limit the number of CPU cycles each container is allowed to access. by setting a limit that keeps each instance of the application performative. We can then balance these sessions so that no user has a bad experience when they're running their code. And so now that we've talked about these security and resource concerns, I'm just going to talk a little about our system architecture. And the decision to implement these containers and connect each user with the session solved some of these security problems, but it presented some interesting engineering challenges. Since now we need to connect each user to their own container, and we need to manage some session data that allows us to do that. And finally, we need to make sure that we can handle the persistence operations that we want to support for our notebooks, such as saving and cloning and loading notebooks. And our solution here was to build sort of a central hub for our system that we call the dispatch server. And it has three main functions that I'll talk about briefly in this section. One, it works as a reverse proxy. Second, it handles all of our session and container management. And third, it centralizes all of our database interactions. And this is just an overview to see our whole system. So here in the front end, we've got our React client, and it does all of its communicating only with the dispatch server. And then the dispatch server on our internal network then handles interactions with Redis, where we manage our session data and that webhook buffer that Charles mentioned earlier. The dispatch server also centralizes all database interactions for our notebook and webhook data. And finally, the dispatch server stands between the client and each of our containerized applications. So now that we're connecting users with containers, we need to find a strategy for doing that. A naive solution to this would be to use port forwarding, where we basically assign each session a unique port on our system, and we map that port directly to the IP and internal port of a container. It's a simple solution, but has a big drawback that someone can scan all of the available ports on our system and then pretty easily have access to any session and disrupt the privacy of that session. And we really prefer not to expose all these ports. So our solution was to implement a reverse proxy, which basically is the only point of contact for each of our clients, and then does all the work of forwarding our HTTP and our WebSocket traffic to the appropriate containers. And in doing that, it masks all this internal information of the containers that we don't want to expose. And just to walk you through how that process works in our system, we've got our React client here that is going to send a code processing request directly to our dispatch server. The dispatch server then uses the session data to forward that request to the appropriate application server inside a container, where that code is evaluated, a response is generated, and then the response goes back to the dispatch server. And then finally, the dispatch server does the work of proxying that response on to the client. And next responsibility of the dispatch server is to manage our session and containers by communicating with Redis, and then also by using the Docker Remote API to create containers as needed, and then when sessions are terminated, to tear them down so that we can free up our system resources for the next user. We need a way to map each user to all this internal system information, like our container IP address and the ID of the container. And our solution was to give each user a unique URL, a subdomain URL, that they then use for the remainder of their session. And by generating a sufficiently unique address for them, we guarantee that that will remain private. And once we've done that, then we need to have somewhere to store and access the session data, since it's then used in every subsequent proxying request. And in our initial prototype, we just stored that in our dispatch server. We just had it as a JavaScript object in memory. Kept our code really simple, but the downside was that if our dispatch server were to crash, or if we had to take it down, we would lose all those sessions and they'd all be terminated. So a better solution was to implement Redis, which as an in-memory key value store is still really fast enough to do the proxying. But it has much stronger persistence, and the only downside being that now we need to add a little code complexity to manage Redis. And then the final function of the dispatch server is to serve as database middleware. For security reasons, we don't want to have each of those application containers communicating with their database directly. So instead, they talk to the dispatch server, which then does the work of communicating with MongoDB. This also, the dispatch server stands up as an endpoint for our webhook data, so that it can always receive that data and do the work of storing it in the correct notebooks document in Mongo. And then finally, the clients send all of their save, clone, and load requests to the dispatch server, which then handles all the Mongo interactions. And finally, I'll just talk about why we chose MongoDB for a database product. Our notebook data is very self-contained. There's no relational connections between one notebook and the next. So that's a good fit for this kind of NoSQL database. It's got a really minimal ORM layer, meaning that we keep all of our notebook data in a JavaScript object in our top-level React component. And so that's a really close fit to the Mongo document model, which is like a nested JSON object. And finally, Mongo has a really flexible schema so that we can expand in future directions. And finally, just want to talk about our future work that we hope to complete. We would like to add an optional user login feature so that people who have a lot of notebooks could organize them more easily. We'd like to add support for more languages in the future. And finally, we'd like to improve our existing testing suite. And this URL here is the URL for our hosted version, so you can go to this and give our notebooks a try. And that brings us to the end of our presentation. I'd like to thank you for listening. And once again, the RedPoint team is myself in Portland, Will in Toronto, and Charles in Denver. So again, thanks for listening, and we will now take your questions in the Q&A feature of Zoom.
I'd also just like to point out, if you guys enjoyed this presentation, that there will be another presentation in about an hour by the Mothership team, and they developed an open source platform as a service, and it's really interesting. So I hope you guys tune in for that.
There are 2 questions in Q&A, guys, and 1 in chat.
Okay. RedPoint Notebooks page cannot be found. Is there a www subdomain in front of RedPoint Notebooks? We're using HTTPS, and so the certificate may be having issues with without having that subdomain there.
I'll pick up another one of these questions. Juliet asks how we decided on using React for a client application. The answer is that React is a really great fit because we have this very dynamic interface where we need to be able to add and remove code cells and markdown cells dynamically. And React is just a great fit for that because you can create one component and then use that same component multiple times inside the application. And as I mentioned before, it's also, by keeping all of our notebook state in a top-level component, it's really easy to then serialize that state and send it over to our backend. And got a question, how long did we spend in design and research? One of you other guys want to take that one?
Yeah, I'd say it took a number of weeks just exploring computational notebooks as a whole, and we had been trying to tweeze apart some areas for, not for improvement, but maybe an expanded use case for certain tools in that notebook realm, but ultimately decided on creating, what you see here, that is a notebook more geared towards developers, as they're pretty data science-y.
Yeah, just to add to that, we initially got really interested in this open source project called Papermill, which is used by Netflix to run their cron jobs as a way of kind of logging some of their analysis of their data, and it's a way of kind of parameterizing notebooks to be run on a regular schedule so that you can see and capture the inputs and outputs and the actual code execution. And we investigated that for a while. but then ultimately decided to back off from that approach because the use case was a little bit of a stretch for us, as we're not data scientists, we're programmers first. So we started exploring computational notebooks more in depth and trying to find a use case where it made sense for us to enter. But we just found the technology really fascinating, so we're pretty interested in that quite early. Are there any other questions?
Yeah, Juliet asked, what decided you on using React for your client app?
I actually already answered that one, Serge.
Oh, okay.
Oh, well, just for the people that can't see the text, yeah, we actually did our initial prototype in vanilla JavaScript, and then we found that just React allowed us to, first of all, keep all of our notebook state in one place at the top level in a top level component, which would make it really easy to extract that data to persist it somewhere else so that we could just hydrate these notebooks on demand. And that way, what we actually save is quite a small file, just a small JSON file. We just found that the React was a good fit for having a dynamic page where you're adding and removing code cells, changing their languages on the fly, and some other sort of responsive features that made our app feel a little bit more like a native app, despite being a web app that's living in the browser.
So here's a really good question. What was the most challenging part of our development? I'm curious what you guys are going to say.
Yeah. I'd say when we were getting close near the end and we were working on our deployment, working with containerized applications and building lots of Docker images. I don't know that it was the most challenging, but maybe iterations on the project felt a little slower moving.
Nathan has a similar question here. It's what was the most challenging, but what part did we enjoy the most? Personally, I have to say that writing the dispatch server code was incredibly satisfying. Didn't really mention in the presentation, but we considered existing solutions, but we ended up writing that pretty much from scratch. And just being able to add all this different behavior and have it handle so much responsibility was really satisfying to me.
I would agree with that.
I found just the error handling and slotting errors, that was a big challenge for us. That may not be quite that obvious, but the delimiter strategy that we came up with wasn't the first strategy. Sorry, welcome to Toronto. The delimiter strategy was not our first idea, and our original ideas were we really wanted to wrestle with that top-down cell execution because we felt in playing with Jupyter Notebooks that it was pretty easy to just forget to run a cell. And the examples we showed are pretty trivial, but it's actually quite easy to get yourself tangled in state, and then you have to reset your notebook and start again. But yeah, our initial strategy was not very efficient, and it was quite a struggle until we kind of came up with this other strategy. And also, I don't know if Charles wants to talk about just error handling, but syntax errors where the code doesn't run and just figuring out how to handle different types of errors was.
Yeah, that was a big struggle was since the rendering of output and standard error from a script depended on that script being executed. If there's an error encountered during parsing of the code, such as a syntax error, it would automatically render it under the first code cell. So we needed to come up with an alternative strategy for parsing errors to determine which cell was responsible for a syntax error, for example.
We've got a couple questions here about the challenges and what we learned about working as a remote team from Gary and another person. And I would just like to say that I thought working on a remote team was really great, especially after launch school where the journey can feel lonely at times. Sometimes you do line up with other people, but then maybe they move ahead of you. But the Capstone experience of having this team was just so cool. Did a lot of pairing on this project, either two-person or even sometimes three-person pairing for really tough problems. And it's such a cool way to bounce ideas back and forth, have people catch mistakes that you're making, and just learn a lot from the other guys on the team.
Yeah, just to add to that, honestly, one of the biggest challenges is just that we'd spend so much time solving problems together, and you spend 50, 60, 70 hours with them, and then the weekend comes and you're like, all right, I'd like to go let's have a beer and just be humans again, like away from work. And that just wasn't possible. But also in terms of splitting responsibilities, we would generally have an agile process. So we'd meet in the morning and talk about sort of what we worked on yesterday, what gave us problems. And then we discuss the sort of the plan for the day. And if there was a particularly difficult challenge, we would usually huddle together and sort of come up with a plan together. And then maybe one person would take that and run with it. And if they needed help, would call one of the other or both of the other people in to resolve it. Or if they could just take care of it on their own, we'd then go review it with a pull request review afterwards. So it was really, really collaborative. There was nothing really that any of us did particularly without feedback from the others. Yeah, thanks for these questions, guys.
Yeah.
Really happy to have you guys here and listen to our talk. Are there any other questions that we've missed?
Yeah, we've got some in the Q&A.
Sorry, Mark, if you could send your question again, I think it might have gotten dismissed accidentally. We've got a question from Stephanie about what we mean by hydrating a notebook. Charles, you want to take that one?
Yeah, and Mark's question was, given the vast possibilities of possible projects, how did you decide to tackle this topic?
Gotcha.
So by hydrating a notebook, that usually just refers to bringing in data from our data store. Hydrating a notebook meaning we've got a notebook cell with some API data. Or if you hit an API endpoint, we've hydrated a cell in the notebook. I suppose it's sort of a term we've invented, maybe. Maybe we should readdress that for future presentations.
Yeah, it just basically means you have this sort of empty skeleton which you fill with data and then it renders in a pretty way.
Mark, to take your question, and also John had a question about why we looked into computational notebooks. I think one of the main things that happened, Will showed you in the note-taking examples, the Quiver application. And in our particular Capstone cohort, one person started using that for their Capstone notes, and then everybody sort of saw it and thought it was really cool, started using it. But as you use something like that, which is like so close to a computational notebook, but you can't actually run your code in it, we were all like, man, the only thing that's missing here is if you could just like share the code and run it right in that same document too. And then we're like, oh, you can. There's this whole world of these computational notebooks. And then once we started to research them, we found them just really interesting. And we wanted to learn more and then decided to build one. I think that might have answered all the current questions. If we missed any, oh, here we go. Jerry asks, how do we go about researching the other computational notebooks? One of you guys?
How did we, or how would you?
How do you go about researching the other notebooks?
Frankly, you just, Google around, you search for their names, you search for computational notebooks, you follow all the links. Some of them we got references to. If you're ever using NPM packages, we found out there's a little button on the bottom that says test it out with RunKit. So RunKit's another computational notebook. And you just basically fire them up and play around. You read all their technical blog posts and just play with it for yourself and sort of see how they handle different situations and just do your research, any way you can. In terms of computational notebooks, Observable HQ and RunKit are both fairly new entrants into the field. Traditionally, Jupyter notebooks are sort of the big player, and they were inspired by this proprietary Mathematica computational notebook, which is, read up about that on Wikipedia. Apparently, it's super genius, started the whole thing. But yeah, it's really just searching around a lot. It's not something I was aware of at all until we started this project.
And to answer Mark's question, the dispatch server is written in JavaScript.
We used a couple of node libraries. There's a node proxying library that we leveraged for the dispatch server. So that's in there too.
Yeah, and if you guys are interested, we did a whole write-up, and we'll have that posted in the next day or two. That really explores all these topics in much more depth. It was a bit of a challenge actually to reduce the challenges we faced into a coherent narrative to present to you guys, because sometimes it was just way too detailed, and we felt that it wouldn't be that beneficial to present about that. But if you have more interest, please check out our case study. Had a lot of fun writing that.
Ryan asks if we have future plans to add code completion. That would be a cool feature. Hadn't really considered it, but it could be a nice addition to it in the future. So the answer is yeah, we would consider that. And Drew asks what role the instructors played and how much guidance they provided to the project. And that's really sort of has to do with the way that Capstone is organized. The instructors really, I wouldn't say they're hands-off, but they're really more just there in an advisory role. Definitely not hands-on in terms of the day-to-day coding, but more just like helping you, especially in that early stage of when you haven't chosen your project and you're, have all these directions that you can go in, helping you to sort of guide, that process and as you narrow in on a project. But then really once you get going on it, they're just sort of checking in, and it's mostly just the team.
And Mandy, you will see a link to the GitHub repo, and in that write-up we'll share in the next couple days.
I'll just throw that in.
The most rewarding part of creating this project was, as Ben kind of stated, it's been super fun to work with a few other people. Even as long as some of the days have been, I'd say that was the most rewarding part, was finally kind of getting out of our shells a little bit and being able to collaborate on something.
We've got a question from Gary. How did the core curriculum prepare you for some of the Capstone challenges? I think the answer is extremely well. A lot of what we had to do was just learning about new topics really quickly. It was like, okay, we need to write a reverse proxy server. Like, okay, we're doing that now. And without the core, sort of like just the fundamentals that we built in core curriculum, I don't think we ever could have, like, in the time period that we had to do this project, gotten up to speed on so many different areas, from networking fundamentals to, writing the code. So it was really totally crucial.
Yeah, just to add to that, before I started the Launch School core curriculum, I was a cabinet maker, and I had no coding experience whatsoever. Maybe like some 1995 HTML StarCraft webpage. So like I had nothing. So basically whatever I've been able to do and learn, I owe to Launch School for being such a great resource for teaching and learning.
Yeah, ditto here. I was a baker. So it's all pretty much Launch School.
Yep.
All right, well, thank you guys very much for tuning in. I really hope you guys tune in for the mothership presentation. We got a sneak peek, and it's super, super interesting. So hope we see you guys in about an hour, unless there are any final questions.
All right, thanks everybody.
Thanks.
Thank you. Take care.